Okay, here we are in our second set of notes in Unit 3, which is on effects, so audio effects. And this is going to be on filter-based effects. So in the previous note set, we saw a bunch of effects that were based upon a delay line. So they were delay-based effects. And one of those was delay or echo. But then we saw flanger and chorus and doubling. So we saw a few others. In this one, we're going to look at filter-based effects, and one of the ones that we'll see is the phaser, which is similar to in sound to the flanger, but we've got a couple others, or at least one other before we hit that. So here's some readings for you. One is out of the book by Reese and McPherson, and the other is out of the DAFX book edited by Zolzer. So maybe you're following along in those. I don't know. So the only two filter-based effects that we're going to talk about, there may be some other ones, but these are the two big ones that are based upon filters. So the first one is the wah-wah, or the wah-wah pedal, although we'll see a version of it briefly that does not require a pedal. And then the biggest one is perhaps the phaser. And like I just said, it's similar in sound to the flanger. In fact, sometimes it's hard to tell whether it's a phaser or a flanger. If the flanger is set to just a slight, very subtle flange effect, it can sound like a phaser. So anyway, the big difference is the flanger is based upon a delay line, and the phaser, as we'll see, is based upon filters, and in particular, all-pass filters. So, but first, let's take a look at the wah-wah pedal. What it does is right there in its name. It makes your sound go wah, wah, wah. So those are sounds that we get by changing the shape of our mouth as we say a vowel sound. So vowel sounds are voiced sounds. You're using your vocal cords, and then the shape of your mouth makes basically a physical acoustic filter. And as you change the shape of your mouth, you are accentuating different frequencies and suppressing or attenuating, at least, other frequencies. And as you change the shape of your mouth, you're changing, as a function of time, the filter that's applied to your vocal cord sounds. So that's how we make the sound wah, wah, wah. If you can try it, you'll see that your mouth makes a very particular changing shape while you're saying that. But it also was intended to mimic the sound that trumpet players got with, well, typically with like a toilet plunger over the end of their horn. They would put it at the end of the bell, the opening of the bell of the horn, and they would rock it back and forth, open, close, open, close. And that did essentially what a mouth does when it's making these sounds. And you could make your trumpet make a wah, wah, wah sound. Trombones do it also. I have not seen it on anything other than those two, but maybe some other ones. I don't know, French horn, flugelhorn, maybe, I don't know. But for us, for digital audio signal processing, we're interested in mimicking the effect box that was developed in the 1960s and applied to primarily guitar. I suppose you could use it on other things. But it was a pedal that had a rocking pedal back and forth that you would control with your foot, and you would use that position of the pedal to set the resonant frequency of some sort of filter. And typically it was some sort of band pass filter, although you could do a low pass with a very high resonant peak that was swept back and forth. So that's the idea. And so somebody invented this back in the 1960s using analog electronics, and we'd like to try to mimic that with digital audio signal processing. And I'm not going to go into a lot of the details of this, but we'll hit some of the high points and give you enough to think about how this might be done. There is a lot of detail on the analog circuits that do this at that website I mentioned before, electrosmash.com. And here they're analyzing a particular wah-wah pedal, the Vox V847, which was one of the early ones, if not the first. I'm not sure it was the first, but it's a very classic wah-wah pedal. But you can see the range. They're showing the frequency response, and you can see that this is in fact a bandpass filter of some sort, and you can see 1, 2, 3, 5 different positions of the center frequency, or in this case, center frequency, but you can also think of it as the resonant frequency of that filter. And so those are just 5 positions. As you rock the pedal back and forth, it would continuously sweep between these. And I'm pretty sure they're showing the lowest and the highest positions that could be achieved, and then 3 intermediate positions. And so over here, I've noted the range of the resonant peak, the range over which that resonant peak can be swept for the Vox 847. And so 450 hertz, that looks about like where that is. It's a little hard to read this. Up to 1.6 kilohertz. So not a huge range, but that's it. And then other wah-wah pedals are going to have other characteristic ranges. Now, that's not the only thing that's different between these, but that's one important thing, and that's one thing that guitar players look for. So the Dunlop Crybaby. So the Crybaby was not initially developed by Dunlop, I don't think. I think it was acquired by the Dunlop company. And the Crybaby might have been the very first one. I'm not really sure. I can't remember the history of the wah-wah pedal. But that's another version of this that you can buy today still. And you can see it goes a little bit lower and a little bit higher than the Vox 847. And there may be some other characteristics that are different, slight differences in shape and other things like that. And we'll talk about some of those other characteristics on subsequent slides. And then John Petrucci, famous guitar player, has a signature wah-wah pedal. I'm not sure who makes that. Maybe Dunlop makes that. And you can see that he pushed the extremes even further. So the low goes all the way down to 100, and the highest position goes all the way up to 3.2 kilohertz. And I noticed that I used capital K here, and I should have used lower k, but that's okay. Little typo. So that gives you an idea of what we're talking about. Now, again, we're not going to go into a lot of the details of how exactly we do this, just kind of hitting the main ideas. So here's a figure from the DAFX book, kind of giving you an idea of how this might be done. So you've got a variable bandpass filter here with a mix control, and they do show a direct going in. This Vox 847 doesn't look like it has any direct in, and I don't think it has a mix control. So you could just eliminate this path if you wanted to, but this is just a little more general. And you could set the mix to 1, in which case this would become 0 and that would be gone. So it just gives you an extra control. But the key control is this right here, a band pass filter that the resonant frequency can be adjusted by the position of a pedal. Now, there's also some indication here that you might be able to adjust the width or the Q. So it's probably more common to set the Q and let the bandwidth change as the center frequency is swept. So there could be a Q control on the wah-wah pedal. And I don't know if I don't think either of those do. The Petrucci might have a Q control. I've seen some of the more signature wah-wah pedals have a Q control on there, but that's the idea. So we already know how to make a filter like that, right? We talked about the state variable or state space based filters that we looked at in a couple note sets back, the last note set of Unit 2. So you could just use those to make a reasonable wah-wah pedal. Now, would it mimic any of these? Probably not. Would it sound okay? Probably yes. But if you're aiming to mimic something that's going to sound exactly like a classic wah-wah pedal, then you do need to go into the innards of those wah-wah pedals to see. Now, we're not going to do that in detail, but we're just going to mention a couple things. So some of the nature of these analog wah-wah pedals rely on some of the nonlinearities in the analog circuits. So there's transistors in there, and I don't think there's a huge nonlinearity going on in the analog pedals, but there is some nonlinearity. Transistors rarely are perfectly linear, so there's going to be some nonlinear aspect in there. So we'd have to mimic that, and we're going to punt that down the road. We'll talk about how to mimic nonlinearities in digital audio processing, that when we're trying to mimic nonlinearities that occur in analog circuitry and mimic those with digital audio processing. We'll talk about that later I think it's in this note set, or in this unit, but at the end. So we'll talk about that then. And then there's also nonlinearities in the inductors used in the wah-wah pedals, and that I know is a true reality. Now, I know you might be saying, and especially since I put it over here, well, wait a minute, inductors, I thought they were linear components. If you go back to your circuits class, everything in your circuits class was assumed to be a linear component. Resistors were linear, capacitors were linear, inductors were viewed as linear things. Yeah, inductors involved derivatives, but they were still linear things. So if you apply the concept of a linear system that you learned in your signals and systems class to the relationship between voltage and current in an inductor as described in your circuits class, that's a linear thing because it depends on either a derivative or an integral, depending upon which way you're relating the voltage and current. And you know from your Calculus 1 class that derivatives are linear and integrals are linear. So you learned that inductors are linear, but they are in fact physically nonlinear. And so the nonlinearity comes just from the physical limitations of how the inductor is built. So inductors are typically built with wire wrapped around an iron core of some sort. If you look into the physics of this, you can find the so-called BH curve. And I'll show you a picture in just a minute and explain what the B and the H are, but maybe you remember. But because of the physics of wire wrapped around an iron core, there are two mechanisms that lead to nonlinearities in inductors. So one is saturation, and again, I'll talk about this when we see the picture below. And the other one is something called hysteresis. So that's a hard word to pronounce. It's not hysteresis. It's hysteresis. So that's a long E, hysteresis, and that's where you put the emphasis on that syllable with the second E as a long vowel sound. Okay, so here's a picture. I just put the web address down here just as a means of citing where I got it. You don't have to go there. But you could go online and read more about the physics of inductors and learn about this. But here's the basic idea. We've got a BH curve. So we've got B up here. That's the actual magnetic flux. So that's something that characterizes the strength of the magnetic field. And that's the field that's going inside the coils of the inductor and through that iron core. And what's making that magnetic flux? Well, it's the current that's flowing through the coils. But it also depends on how many turns, how many coils you have on that inductor. So the magnetizing force is the H variable. That's the thing that we control by shoving current through an inductor with a certain number of turns. The number of turns in this setting isn't really controllable, so we control the magnetizing force through the amount of current that we put through it. And then the amount of inductance that we get is set by the resulting magnetic flux. And so that will control how the inductor behaves like an inductor. But we see that it's not just a proportional relationship. So if we wanted this to be linear, it would be some sort of line that would go like this. And so if we doubled H, we would double the amount of B that we got. But here's the thing, because of the actual physics of this, the curve that the B follows as we adjust our current to get the magnetizing force follows a weird kind of S-shaped thing. Almost looks like the F hole on a guitar. So that's one way to think about it. But suppose we started here. Actually, if we first start off, we would start here. We've got zero current flowing through it, and we get zero magnetic flux. And then as we increase the current in one direction, we would move this way on the H, and we would follow this curve. Notice that that's not a straight line. It kind of curves. And that's due to saturation and just the physics of the exchange between magnetizing force and magnetic flux. So even that part is nonlinear, right? So we get to a certain point and it saturates. Any additional current will not give us any more magnetic flux. And again, that's just due to the physics and maybe some of the imperfections in the iron and so forth. To be honest, I don't remember enough of my physics to say exactly why that happens, but I do know that happens. So you get some saturation. And then here's the curious thing. So you're up here, let's say we got up to this point, and now we're going to reduce our current. We don't come back down the same path. Nope. That's where the hysteresis comes from. We go back down some path like this, and here's an interesting thing. We get to zero on the current, and we still have some residual magnetism. So, that's, I think, kind of along the lines of if you take like a steel screw or a screwdriver perhaps, and you bring it in contact with a magnet, and then you take the magnet away, you can get the screwdriver to have some residual magnetism. That's the same kind of thing that's going on here, I believe. But nonetheless, I do know that these inductors do follow these hysteresis curves. So then as we continue to change our current, if we make it go negative, so remember that's just going in the opposite direction, we continue to follow this curve, and eventually as it gets more negative, we will start to saturate in the other direction. And then, and this would just continue on at this level here if we went to even higher currents. Now we bring the current back, start reducing it in this direction, and heading back to a current of zero. We don't go back on that same curve we came down, we go on some other curve. And again, that's due to the residual magnetism of the core. And so once we're operating, we never go back onto that starting curve. We're just constantly going back and forth on this kind of F-hole shaped curve. So that's called hysteresis. Both of those effects, saturation and hysteresis, are shown on this curve, and they both contribute to the nonlinearities of inductors. And wah-wah pedals, by the nature of their invention were built originally with inductors. You can go to the Electrosmash website to see the circuit and learn more about it. I didn't spend any time on that here. But the point is, and they do talk about this on the Electrosmash webpage, those early wah-wah pedals used a certain inductor that came from Italy at that time. And it was probably just one of these things where the person who was building the initial circuit was just like, hey, I need an inductor. Oh, I've got one here. It happened to come from Italy. There was nothing special about it at the time. They threw it into the circuit, and then people liked how that sounded and discovered that if you put in other inductors, I'm not talking about different values. I'm talking about different manufacturers of inductors, right? Slightly different iron core makeups and slightly different geometries of windings and so forth would all lead to different shapes of hysteresis curves. So certain inductors are going to have certain sounds because of that in the wah-wah pedal. And they became very celebrated in the sense that people will talk about a particular type of inductor that you have to have in order to make your wah-wah pedal sound good. So you can go down that rabbit hole if you want. They talk about it at the Electrosmash entry for the Vox wah-wah pedal, but there's thousands and thousands, I would guess, of web pages where people talk about these. But here's the point. If we want to digitally mimic a specific wah-wah pedal that was originally done with an analog circuit, you need to mimic the exact nonlinearities that are in there. So you should find out what kinds of transistors are in there and then use the techniques we'll talk about later to mimic nonlinear circuit elements. And you should also do the same thing for the inductors. Now, we don't talk about how to model nonlinear inductors later, but the ideas that we use, we'll focus mostly on diodes. The ideas that we use can certainly be used to model the nonlinearities of inductors as long as you can describe that nonlinearity mathematically. Then you can put that into your mimicking digital processing to do that. But that's the idea. So, like I said, you need models. So we might try to do this mathematically, but we might also just measure these. So a lot of the companies that make digital audio mimicking devices will talk about how they got a hold of classic things and they've put them in the lab and they've measured them and they've characterized their performance, their curves, whether they're linear curves or nonlinear curves. And then they've imparted those models into their digital processing. So we can't go into all those details in this course, partly because of just time and partly because that's not something I have ever done. So I don't really know exactly all the details. And those companies hold those ideas pretty close to their chest. They're not going out and publishing exactly how they do those things, but they are letting you know that they do those things. So anyway, we'll talk about some of that, at least from a high level point of view later on. So that's the wah-wah pedal. And then there's something called the auto wah. So not to be confused with Ottawa, which is the capital of Canada. I can never resist making that bad dad joke on this slide. So it's just like a regular wah-wah pedal. Circuit is the same, except how the frequency, the resonant frequency is controlled. So with the regular wah-wah pedal, you've got a pedal that the player rocks that back and forth, and they're perhaps able to rock it in sync to the music, to the notes that they're playing. So it gives an awful lot of control. But here's the idea. You could just use an LFO to sweep that center frequency. So, in an analog setting, that might be a little bit more difficult to do. But in a digital setting, that's extremely easy. We've got the state space filters that we talked about. We can control with an LFO. We can control the FC in that, and that would be able to sweep this back and forth. So just like we saw for the flanger where we would sweep the delay back and forth with an LFO, we can sweep the resonant frequency of the bandpass filter back and forth. So that's one way, but it's not necessarily the most common for the auto wahs that are available. The other is that the center frequency position is controlled by the output of something called an envelope detector. Now, we'll talk about that in much more detail in the next set of notes in this unit when we talk about compressors and limiters and things like that, things that control the dynamic range. So when I say compressor here, I don't mean like MP3 compression. I mean like an MXR dynamic range compressor, something like that. So inside those circuits is something called an envelope detector. And like I said, we'll detail that in the next set of notes. But basically, it's giving you a voltage that follows the loudness of the signal. So if you're playing along and you pick strongly, the envelope detector will give you a large value out at that instant that you picked strongly. But if you pick weakly or right after you've picked strongly, the envelope detector's output will be lower. And so now you use that changing voltage to sweep the frequency of the bandpass filter. So it's usually set up so that the louder parts of the signal will push the center frequency up towards the ah part, and then the quieter ones will be more down towards the whoa. So if you were to play loud, start soft and get loud, it would go wah. And so it becomes interactive with your playing. And so, like I said, in a regular wah, the player has to rock the pedal to be in kind of sync with the notes that they're playing. And auto wah kind of does that on its own. So here's a picture. This is just a little snippet of an audio file of me playing guitar. If you had access to this and you zoomed in, you'd see lots of this wiggles up and down. So it looks kind of like it's solid and filled in to some degree here just because I've zoomed out quite a bit. But that's where the signal's just wiggling up and down, very, very fast at, reasonable audio frequencies. And the red curve on the top and the red curve on the bottom are exactly the same. So these things will be clearer when we get into the next set of notes. But basically, the red curve is following the loudness of that music. So it gets loud here at first. That would be when I first picked a note. And then we see that the envelope decays down, and then it's loud, and then it decays down, and loud and decays down. So and it starts off not very loud. So if we looked at just this, we would see it go wow, 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 wow. So that's kind of the idea. And so that's how an auto wah would work on this. So that's about as much as we're going to go into details on wah-wahs. Again, the starting place would be to learn how the analog circuits work. Go right to electrosmash.com. I have no connection with them other than I go to that webpage a lot. And then once you learn how the analog circuits work, you can break those apart and find out how to mimic this in a digital way. Okay. The rest of this note set will be focused on the phaser, and we're going to go into a lot more detail on that. Like I said, it sounds a lot like a flanger, and sometimes it can be difficult to tell which one is being used, especially if they're both set to a subtle effect rather than a very strong effect. So remember, we had that depth of the notches setting on the flanger. We'll see a similar kind of thing. So how are they different? Well, they create their notches. They're both based upon notches, but how they create those notches is quite different. And how many of those notches there are is different. And how the notches are located relative to each other. So the spacing between the notches is different for a phaser than it is for a flanger. And so that's what makes them sound different. But they're still both basically sweeping notches and peaks through frequency. So just a reminder, here was the flanger. We had this time varying delay going on here driven by an LFO. And we hit it with a G factor, which really can be limited between 0 and 1. And when it's set to 1, we get the most destructive interference between the output here and the regular signal, the original signal coming through, and then adding together. So that would lead to very deep notches if G was set to 1. And we analyzed that. We saw that we needed to use an interpolated delay line to get that. And we saw that this was nothing more than a time varying comb filter. So if you freeze the LFO at a particular point, you'll have a particular delay there. You'll have a particular comb filter there. And what we saw was that the notches in the comb filter are uniformly spaced. And the spacing is inversely proportional to the amount of delay that we have. So that's the flanger. So you get equally spaced notches, and there's lots of them. It goes basically from 0 all the way up to your FS over 2. So based upon the spacing, we'll determine how many you have, but you usually have a lot of them. A phaser, on the other hand, replaces this delay line with an all-pass filter. And in fact, it's usually a cascade of several stages of all-pass filters, and usually those stages are second order, and we'll see why. But the idea is that at frequencies where this filter will give you 180 degrees phase shift, or any odd multiple of 180 degrees phase shift, then the signal here and the signal here are perfectly out of phase at that frequency. And so if the depth is set to 1, then you have complete cancellation at that frequency where this filter has a phase shift that's an odd integer. I may have just said integer multiple, but I mean to say odd multiple of 180 degrees. So when we have an odd multiple of 180 degrees there, at those frequencies, we'll have notches. And we'll see when we analyze this that the structure, the spacing of those notches is going to be very, very different than what we had in a flanger. So 2 different ways of making those notches. For the phaser, no surprise, the word phaser comes from the fact that we're making notches based upon phase shifting, and we use all pass filters to impart that. So I say that here, odd multiple of 180 degrees. I might have misspoken just a minute ago. So that's the idea. So let's take a look at this. Let's remember our second order discrete time all pass filter. And again, you can learn about the analog versions of these things by going to the electrosmash.com webpage. I think they analyze maybe the MXR phase 90, which was one of the first and classic analog phasers. Anyway, here's our discrete time second order all pass filter, and its coefficients have that classic reversed in time nature, and everything is set by just the 2 numbers C and D. So D is completely set by FC. C is completely set by FB. Now we might really want to have that set in terms of Q, so we could do that, but now there's going to be an interaction between C and D, but that's not a big deal. So the LFO is going to control that FC. So if we don't want this thing to have constant Q as we change it, as we change FC, then we only really need to adjust the D. So we would just be adjusting this inside coefficient. But we might also want to have the Q stay constant, so we'd have to change the FB as well. It would just depend on what you're trying to accomplish. We also saw that discrete time all-pass filters have this relationship, this reciprocal relationship between its zeros and poles. So we think about these two being related, but in reality, due to the details of complex numbers, this is actually the reciprocal of that one, and this is actually the reciprocal of that one. But remember, these always must appear in complex conjugate pairs, so it doesn't really matter if we think about it as these two are related to each other and those two are related to each other. Okay, so we've got that, and we looked at a plot of the phase versus frequency, and in this case I did it for an FS of 44.1, so right here at 22.05 is where things cut off due to that. I mean, technically it would repeat, but I'm only showing it up to FS over 2. And remember, for the analog one, this actually much more smoothly goes asymptotically to minus 360 degrees. This squishing in is due to the effect of the bilinear transform, the warping. So we saw that before. And here I've got my FC set to 5 kilohertz. That might be a little bit high for an audio application, but I just picked it to just make a plot here. And here the FB is set to 2 kilohertz. So remember, FB was set by the minus 90 to the minus 270. And the FC is set where it's minus 180. Those were the conditions for the second order. They were a little different for the first order. So there's a plot of that. So as our LFO changes FC, this thing is going to sweep back and forth. This phase thing will the whole curve will change as the LFO changes that. So you'll see at different frequencies, the amount of phase that we get will be changing with time. So here's the idea. So let's just look at a single stage. So one, not a cascade of several second order all pass stages, which is typical, but just one stage. So one second order all pass filter. So here's a rendering of the plot that we just looked at on the previous slide, although now the FC is quite a bit lower. Now the FC is at 1 kilohertz, which is perhaps a more reasonable position to put it. But we'll see the characterization of how to think about where to put the center frequency for this later on. And you can go look to see the positions, the nominal positions of the FCs for the phasors analyzed on ElectroSmash if you want to know what are typical things. So for this one stage of second order all pass, there's only one place where we hit an odd multiple of 180 degrees. That's negative, but that doesn't matter. So we're going to get just one notch. We'll just have one notch, and it will happen at FC. Now, as the LFO changes this, that frequency where we have the one notch will sweep back and forth. So I didn't really draw a picture, but what we would see in this case is something that looks like this. Assuming that our depth is set to 1, we'd see one notch. And I don't know if it have exactly that shape, but this would be at FC. Just one notch. That would not sound terribly interesting. And remember, the LFO is going to sweep that back and forth. You can decide the range that you want to sweep it over. Again, look at the analysis for analog versions of these to get an idea of how far you would typically want to sweep that. So that's the idea. So we're going to sneak up on this. So that's just one stage of second order. Let's look at two stages. So I've just shown the same picture up at the top, and now I'm assuming that in this all pass filter, I've got two stages. So now basically the phase of two stages is just twice the phase of a single stage, assuming that each stage is identical. And that would be the case. All the FCs would be set to be the same, and they would be controlled synchronously by the LFO. So because phases add, and we're basically adding the same phase to itself, that just ends up with getting twice the phase of a stage. So here we see it goes from 0 to minus 720, and over here we saw it going from 0 to minus 360. So now, since we're going with two stages from 0 to minus 720, there's two places that are integer multiples of 180 degrees. And that's where we'll have notches in our filter. So I've put two X's there. So if we were to draw this, we'd have a notch there and a notch there. So this would be at this frequency, and this would be at the frequency where that is occurring. And the other thing that I've notated on here is how we get those. So these phases over here are the phase of a single stage, that each stage that's making up that cascade of two second order all pass stages. So twice the phase, that's where this 2 is coming from. So to get 180, and I left off the negative signs in here, just didn't really need them. To get 180, I need to be at a frequency where each stage was 90 degrees, so that 2 times 90 will give me 180. And then the other notch will occur where the original stage is at 270. So that's what I'm saying here. And this is just a little formula for that. 2 times phi1, so the sub 1 is the phase for a single stage, second order in this case, is going to be k times 180. K is selected to be the odd integers. And I can only do 1 and 3 in this case, because if I went to 5, I'd be beyond the largest phase shift that this two-stage cascade can give me. So that means we can trace back where our notches are going to occur just looking at the phase response for a single stage. So if we go back and look at the single stage, we're saying here we need where it goes to 90 degrees and 270. So if we come back here, this is a little hard to see, but here's 180, there's 90, and 270 is going to be there. So if we draw those over, we can now find where the frequencies will be located. So, roughly something like that's 100, 200, 300, 400, maybe 400, 500-ish, and then 1,000, 2,000, maybe somewhere between 2,000 and 3,000, something like that. So that's very different than a phaser or a flanger with two notches. Go back into the previous note set. I showed an example with just a very small delay with two notches. They were spaced very, very differently. They were spaced uniformly. So from 0 to the notch to the next notch, that notch up to Fs over 2, those were equally spaced for the flanger, but not so here. Okay, so that's two stages. And we have this nice little formula. Remember, the 2 comes from the fact that we had two stages, and that gave us twice the phase. And the K came from the allowable odd integer multiples of 180. So now let's go to 3 stages and 4 stages. So now with 3 stages, we see that the maximum phase that we can get is 1,080 degrees. And we can find the various odd integer multiples of 180. So here's the 1, integer 1, here's the integer 2, and here's the integer 3. So that gives us those 3 positions. So 3 stages will give us 3 notches. And where are those frequencies? Do we have to find this 3-stage phase? No, this is just going to be 3 times a single phase. So if we were to take this, go back here, if we were to take this phase plot and just simply plot it with the phase values multiplied by 3, we would get this phase plot. And so now we can say that this minus 180 is 3 times what? Well, 3 times 60. And this minus 540 is 3 times 180. And this minus 900 is 3 times 300. Again, I've left off the negative signs there. So now we can come back to our 1-stage thing and say, I forgot the numbers that I need, 60, 180, 300. We can come back here and say, 60, 180, and 300. So those would be the frequencies where we would have our notches for a 3-stage phaser based upon this single-stage phase. Okay, so again, those change as the LFO changes the FC. So I'm just showing at a fixed, nominal value for the LFO. Maybe this was where the LFO is set to 0, but it's going to sweep these things. So we'd have 3 notches, and they will change in position, and their spacing will change as well. And then we go to 4 stages. So again, now we get a 4 here because of the number of stages. And we ask ourselves, 4 times what gives us 180? And 4 times what gives us minus 540? So these are the integer multiples of 180, odd integer multiples of 180 that we need to make the notches. And so here's a simple formula for that. Notice that we always had the number of stages multiplying the phase on the first, the single stage, second order single stage. So the subscript 1 here is the phase for 1 second order stage. And instead of putting the n out in front of that, I've swung it over to the other side. And then here is the k times 180. I should have a comma in there. So that's not 180 times k twice. That's just saying comma, k takes on those values there. And so they're going to take on, the k is going to take on the odd values all the way up to its largest odd value allowed, and that will be 2n minus 1. So you can check that that works for the first stage and for the 1-stage case and the 2-stage case, and then you can check that it works for 3 stages and 4 stages. That just tells you how many notches you're going to get. So you will get 2n minus 1 notches. So let's plug in 4. So that's not how many notches. I just misspoke. That's the largest integer that we'll get, but we're going up only in odd. So we would go, for the 4th stage, we would go up to 7. So it'd be 1, 3, 5, 7, 4 notches. So that's how you figure that out. So now you can deduce for the number of stages that you have, how many notches. And it will always end up being, for a second order in each stage, you'll get a notch per stage. So again, just reiterating the differences between the phaser and the flanger. A phaser has a small number, and that's a fixed number of notches. And those notches are not equally spaced in frequency. Whereas the flanger has a large number of notches, and that number of notches varies as you change the delay, because that's going to make the notches either closer together or farther apart, but you have to have them equally spaced over the entire range of frequencies being processed. So that's the big difference. So they sound similar because you've got sweeping notches, but they sound different because of these different features. So just a word about the LFO for the phaser. You can look to see what the typical frequencies are. Again, just look at the classic analog phasers to see that. And you'll also see that some phasers allow you to change the shape. So it's common to choose a triangular. Well, I misspoke. So in the flanger, you can sometimes change the shape, but in phasers, there's a particularly special shape, and it just works out that that's what sounds best, and it relates to the fact that there's a small number of notches, and we can almost hear where those notches are. So what we want is an exponential LFO waveform so that it's related to how humans hear frequency. So if we say that humans hear this exponential as a triangular in frequency, so what we would want is to use a triangular LFO shape, but we want to understand how we're going to hear that. So we use the logarithm to map that. And so if we specify our LFO this way, using a triangle, this is just equations that tell you how the triangle works. We can then map this mathematical expression into a triangle for a particular given LFO frequency. So if we convert that into FC, what we see is that we use the triangle to adjust the FC in this exponential form. So W is our kind of a width setting. It's F max over F min. And so this would sweep, if we put a triangle shape and we use it using this exponential form to change the FC, then we will hear this sweep in a way that sounds triangular. And so I'm just stating what are some typical ranges for the FC, and so you can work that out if you ever want to make one of these. And then finally, just a variation on the phaser. Just like the flanger, we could include feedback, and here we can put feedback around the cascade of all pass filters. So this would just be whatever cascade we have. And then we can set this to some number. You have to be careful. You want to make sure that this thing stays stable. So you'd have to analyze the range that you'd want to set that. Anytime you're using feedback like that, you need to worry about the stability impacts. So that's just going to make the phaser sound a little different. And so a user could adjust a knob to set this value. And you could set it to 0, in which case you'd have no feedback, and that would just be the standard phaser. So it would just be a knob and or a switch that you could put on your effect. So those are filter-based effects. We talked about the wah-wah filter. We talked about the phaser being perhaps the bigger one that we would be trying to build digitally, although to really do the wah-wah, we'd have to dive into it to really mimic an analog one, and we'll need some things that we'll talk about in future note sets. All right, the next note set up is on compressors, dynamic range compressors. So I hope to see you there.